Hey everyone, welcome to the first video in our series on the reactions of chapter 11. This chapter talks about reactions of alcohols. So this is things we can do with alcohols once we've actually made them. Um, in this video, we're going to be talking about oxidation of alcohols, which there's a lot of ways we can do that. There's going to be like 5 different reactions in this video. I'm going to try to go through this as quickly as I can so that way this video is not a million years long, and I'd like to condense this as much as I can. So we will talk about 2 mechanisms, and one of them is kind of a mess. So we'll we'll see how it goes. Um, like I said, I kind of want to go through this as quickly as possible. So with that being said, let's get started. So like I said, we're going to be talking about oxidation of alcohols. This is alcohol oxidation, and there's 5 ways to do this. Okay, give or take. The very first way we're going to talk about is bleach. Okay, so bleach is sodium hypochloride or hypochlorite. Okay, and that is NaOCl. So bleach. Okay, so if I take say we take a 2-degree alcohol, right, and we put it with bleach, so NaOCl with acetic acid, HOAC. Okay. So if we use a second-degree alcohol with this, I'm going to oxidize the second-degree alcohol. So what does that mean? Well, that means that um, I increase the amount of carbon-oxygen bonds in this molecule. So right now, this carbon is bonded to oxygen 1 time, right? So if I make it bonded twice, well, what does that give me? It gives me a ketone, right? So second-degree alcohols are going to become ketones with this, right? So we are oxidizing it. We're oxidizing it, creating more carbon oxygen bonds. So that's why we turned this second-degree alcohol into a ketone. All right. Let's do another example here. So we'll use this alcohol. And again, we use NaOCl with acetic acid. And what does this give me? Just gives me ketone, right? Cyclohexanone, right? So it just gives me a ketone. We're not going to worry about 1 degree with just regular bleach. There's another reaction we're going to talk about where we're going to start using 1 degree. But I do want to talk about the mechanism of bleach and how bleach oxidizes. Okay, so let's do that. Okay, so this second-degree alcohol here, I'm going to do the mechanism, excuse me, for this first reaction that we've done. Okay, so the first thing we do is we start off with the NaOCl. Okay, and this is negatively charged, and we also have acetic acid in here, right? So we have acetic acid. Acetic acid looks like this. And what this is going to do is this negatively charged oxygen is going to take a hydrogen off the acetic acid to protonate it, right? So then that gives us HOCl, right? And then I also get sodium acetate. So that's Na plus with my negatively charged acetate molecule. And after I protonate it the first time, I'm actually going to protonate it again because that's going to make it a reactive intermediate. So it's going to come up here and protonate this one more time with another acetic acid, right? And then that's going to give me this. And then I also get an acetate, right? Okay, so now that we have this, my second-degree alcohol is going to come in and it's going to actually attack the chlorine on this molecule. So I'm going to write that down here. So the second degree alcohol, which also has a hydrogen here, right? The second degree alcohol is going to attack the chlorine. Okay. So the second degree alcohol will take this chlorine off of here, and then that's going to cause this to leave. Well, this is just OH2, right? Which is H2O, which is water, right? So I have taken my second degree alcohol and added a Cl to it. And it's positively charged now, and I still have the hydrogen on there, right? And I just made water, because water just left from that reaction. So now what's going to happen is this water is going to come over here and take that hydrogen off, right? And then that's going to give me H3O plus, but it's also going to give me this. And like I said, I also get H3O plus. Okay, so now that we have this, what's going to happen is our very last step. So, didn't draw the negative charge there. Sorry about that. So one of these negatively charged acetate molecules that we made earlier is actually going to come back and act as a base. And it's going to take a hydrogen from the carbon that the oxygen's on, and these electrons are going to form the double bond O, which is going to cause chlorine to leave. And then that's my final step. So in this step, I have made my ketone. And I also got acetic acid. And chlorine left, so I got Cl minus. Okay. So this is the full mechanism for how bleach with acetic acid works, right? So first we protonate that OCl twice with acetic acid. And then we form a reactive intermediate that's protonated, and we react that with the second degree alcohol, and then we deprotonate that alcohol after the chlorine gets added, and then we just form the carbonyl group, and the chlorine leaves, and we're done. Okay. So that's how this works. Okay. So there are some variations on bleach that we can do. So we can just use regular bleach with acetic acid, but there's something else that we can do, which is we can take bleach and add it with something called tempo, okay? So if we take bleach and tempo, so let me write this. So this is bleach, and we're not going to worry about this mechanistically. So bleach with tempo, and tempo looks like this. It's a heterocyclic free radical. So yeah, that oxygen is a free radical, right? So this is tempo, all right? And so what happens is if I take bleach and use it with tempo, then I can use a primary alcohol. So earlier we were just looking at secondary alcohols, right? We were looking at secondary alcohols uh, with bleach. So in this case, I'm going to use a primary alcohol with tempo. And if I do this, it's going to turn that OH, as we would expect, into a double bond O, right? So I get an aldehyde, okay? I get an aldehyde. And we can do another example as well. Again, I just get an aldehyde, right? The caveat being that if in this reaction, I need to use a similar amount of bleach and tempo, right? If I throw in a absurd amount of bleach, so let's just do this second reaction again, except I use a lot of bleach. The way that I would say that I use a lot of bleach is by saying excess. So I say excess bleach with tempo. Then what this does is it goes from taking this just to an aldehyde, it takes it all the way to a carboxylic acid. Okay, so it fully oxidizes it into a carboxylic acid. All right. So we go just from an aldehyde all the way up to a carboxylic acid. And that's because you'll notice on this aldehyde here, I have a hydrogen here, right? And this hydrogen, remember that from chapter 8 and 9, whenever we used hot potassium permanganate versus ozonolysis, there was cases where the hot potassium permanganate would oxidize this hydrogen into an OH. Well, that's the same thing that's going on here, right? This excess bleach is coming in with this tempo, and it's fully oxidizing that hydrogen into an OH group, which gives me a carboxylic acid as opposed to an aldehyde, okay? So if I just use regular bleach with tempo, I get an aldehyde. But if I use excess bleach with tempo, then I'm going to get my carboxylic acid, okay? So I get a carboxylic acid if I do that. Okay, so this is everything with bleach, and then I'm going to erase this and we're going to talk about a very strong oxidizing agent next, okay? Which we're also going to do the mechanism for. Okay, so my next one that I'm going to do is chromic acid. And this is also called the Jones reagent. So chromic acid, or the Jones reagent, is a very, very, very strong oxidizing agent, okay? So again, my 2-degree alcohol is just going to become a ketone, but we'll see what it does to primary alcohol. So for chromic acid, I usually throw in chromate with sulfuric acid. And then this makes chromic acid in solution, but just gives me a ketone, right? There is another way that we can write this as well, so I'm going to use a primary alcohol this time. And I'll show you guys the other way to write this in just a second. So chromate, sulfuric acid. In this case, just like with excess bleach and tempo, this is a very strong oxidizing agent. So it's actually going to take this and it's going to turn it into a carboxylic acid, okay? Because this is a strong oxidizing agent. Another way that this can be written is instead of using chromate and sulfuric acid, I can use potassium or sodium dichromate. So that's Na2Cr2O7. So this one is sodium dichromate, right? I could also use potassium dichromate, which is K2Cr2O7 with sulfuric acid. So I can use either one of those with sulfuric acid, and that's going to do the exact same thing. Does not matter. It's just it's two ways of writing the same reagents. And again, strong oxidizing agent, so it's going to give me a carboxylic acid if it's a primary alcohol, okay? The one thing that I do want to mention is that if, let's say I take a 3-degree alcohol here, okay? And this is the case for every single oxidizing agent, okay? So if I use a 3-degree alcohol with, and I'll mention this again at the end of the video, but if I use chromate and sulfuric acid with a 3-degree alcohol, well, let's take a look at this. Let's say I turn that alcohol into a double bond O. Well, how many bonds does this carbon have now? 1, 2, 3, 4, 5. That's illegal. We can't do that, right? So I'm going to erase that because 3-degree alcohols give me no reaction, okay? And that is the case for every single oxidizing agent, whether I'm using chromic acid, whether I'm using bleach with tempo, or the ones I'm going to mention later, PCC, DMP, anything, right? It does not matter. It is just not possible for me to oxidize a 3-degree alcohol. Okay. Okay, so now we're going to talk about the mechanism of chromic acid. So let's take a look at this mechanism. And I'm going to do the mechanism with the secondary alcohol. Okay. So this secondary alcohol should be a little more clear here. Alrighty. So we're going to use this second-degree alcohol. So the first thing that happens is chromic acid is going to get attacked by the second-degree alcohol. Okay. There's going to be a lot of electron drawing in this one, unfortunately, so it's going to take me some time to draw all this. So I do apologize for that. I'm going to try and draw as quickly as possible. My handwriting might suffer slightly. Okay, so this alcohol is going to attack the chromium, and one of those bonds is going to go on to one of the oxygens. Okay, so this one could also go onto that one. It doesn't necessarily matter too much. Okay, so then what that gives me is this intermediate. Excuse me. Drawn it at a weird angle. So I have a hydrogen on there, right? And then this oxygen is going to be positively charged because it has 2 bonds on it. And then I have this. Okay, like I said, a lot of electron drawing. Okay, and this O is negatively charged as well. Okay. So now what's going to happen is an intramolecular reaction. And the way this is going to happen is that one of these OHs here is going to take the hydrogen off this oxygen and then put those electrons onto there. Okay. So what that's going to give me is it's going to give me 2 lone pairs on this oxygen now, and it got rid of my charge. And then everything else is still the same. Except now I have a protonated OH on the chromium. Okay. So now what's going to happen is this protonated OH is a good leaving group. So this carbonyl, or not, excuse me, not a carbonyl, this chromium double bond O is going to reform from the beginning, and then this is going to leave. Okay. That's going to leave. So then what I get after that is the same type of thing, except now I have a double bond O up here and a double bond O down here. And then I have OH. And then my other OH is gone, right? My other OH left. Or OH2 rather, so I also formed water. Okay, I also formed water. And I have a lot of water in solution. So another water, or the water I just formed, just depending on how we write it, can come in and it can take this hydrogen off, okay? This is just like the bleach mechanism, so it's going to take the hydrogen off, and then that's going to form my carbonyl group, which is going to cause the chromium to leave, and then one of these electron pairs is going to go onto there. So now what do I get? Well, I get my ketone. I also get H3O plus. Okay. And then finally, I also get my chromium complex, I guess you could say. So my chromium complex is going to be chromium. This became a O minus. This became a double bond O. I have a lone pair, and I have an OH here. Okay. And then that molecule there can get protonated by H3O plus at some point to get rid of that minus charge as well. Okay. So this is my mechanism for chromium. A lot of electron drawing in this, so it's kind of a mess, like I said, but not too horrible. This isn't a vital mechanism that we really need to know or anything like that either, but I think that it's just interesting to talk about it because there's a lot of parallels between this and the mechanism with bleach, right? So I did want to mention it shortly here. So hopefully it's not too terrible. Okay. So this is one of my chromium reagents. There is another reagent that contains chromium that I can use, and I'm going to erase this so we can talk about that one. So this reagent it was a strong oxidizing agent, right? It's a very strong oxidizer. There's a chromium reagent that exists that is a weak oxidizer. So this one is known as PCC, which is pyridinium chlorochromate. Okay, pyridinium chlorochromate. So the way that I create this is I take chromate, so CrO3, HCl, and pyridine, which is a heterocyclic six-membered aromatic molecule. Okay. And whenever I put all three of these in solution together, what I get is a protonated pyridine, which is known as pyridinium. And a complex with chromium and Cl, which is negatively charged. So now I have pyridinium chlorochromate. Pyridinium chlorochromate, this is PCC. So this is how I make PCC. Okay, so now, like I said, this is a weak oxidizing agent, right? So let's talk about it here. So if I take a second degree alcohol, well, we already know what second degree alcohols make with any reagent, right? They always just make ketones. So I do PCC with CH2Cl2. So this is DCM. So DCM is almost always my solvent with PCC. Very soluble in DCM. So I just form a ketone, right? Just form a ketone with PCC. However, whenever I use the Jones reagent or chromic acid with a primary alcohol, I would get a carboxylic acid, right? But in this case with PCC, since it's weak, I don't get a carboxylic acid. I get an aldehyde, okay? So these 1 degree alcohols become aldehydes. So let's do one more example here. Oh, starting off with an aldehyde, did not mean to do that. So if I take this primary alcohol here and put it through with PCC and CH2Cl2, then I'm also going to get an aldehyde. Okay, so I get ketones and aldehydes from PCC. That's it, right? Okay. So again, not a whole lot going on with this one. Pretty simple. Okay, not too terrible. So this is another one of the weak oxidizing agents that we can use. There's two more weak oxidizing agents that we can use actually. Okay, so I'm going to talk about those two now. So one of them is something that, or is going to be using something we're probably familiar with. One of them is the Swern oxidation. Okay. So the Swern oxidation uses DMSO, dimethyl sulfoxide. And if we remember, dimethyl sulfoxide is a fantastic solvent for SN2. It's polar aprotic. Well, it turns out that it also works well for being a weak oxidizing agent as well. So if I take a primary alcohol with Swern oxidation, and Swern oxidation is 2 steps. in the first step, I use my dimethyl sulfoxide, DMSO, and then parentheses COCl, parentheses 2, and typically negative 78C or negative 60C. Very low temperature, it needs to be at a low temperature. And then as a second step, I use triethylamine. Okay, ET3N, triethylamine. So what it's going to do is it's going to turn this primary alcohol here into a aldehyde, because this is a weak oxidizing agent, right? So it's going to turn that into an aldehyde under these conditions. Again, if I use a second degree alcohol, it's just going to turn it into a ketone, right? So DMSO, COCl2 at negative 78C. Again, this just gives me a ketone, right? Always gives me a ketone with second degree alcohols. So Swarin oxidation, pretty simple, right? Does the exact same thing as PCC. And so if it does the same thing, why do we have it? Well, PCC contains chromium, right? And while PCC works fantastic, the issue is that chromium is bad for the environment, and it's very, very difficult to dispose of properly, and it also causes cancer. So if we want something that isn't going to give us cancer or has a lower chance of giving us cancer, then maybe we want to use a Swarin oxidation. Or if we don't have the means of getting rid of a chromium reagent like PCC, then maybe we want to use the Swarin oxidation, because we can more easily dispose of the byproducts and everything from Swarin oxidation. So those are kind of some of the advantages with things like this, right? Okay, so now we've talked about Swarin oxidation. I'm going to talk about something else that does the same thing again, okay? This also does the exact same thing. And this is known as the Martin oxidation. Okay, so the Martin oxidation uses a molecule known as the Martin periadenane. Okay, so Martin periadenane is a benzene ring with like a 5-membered ring that is like a cyclic ester, and it has like 3 acetate groups on it. It's a mess, right? But that Martin periadenane is abbreviated as DMP, Martin periadenane, DMP. So all we do with this is another weak oxidizing agent. So I'm going to use the same thing I used up top, okay, for Swarin oxidation. So if I use that same primary alcohol there, guess what? It does the same thing. So Martin periadenane, DMP, and then I usually use DCM. I'm going to write out DCM though as CH2Cl2. So DMP and CH2Cl2 gives me the same thing as Swarin oxidation. No difference. Again, if I use a secondary alcohol with DMP, gives me ketone, right? So that's it, okay? So Swarin oxidation, Martin oxidation, same thing, okay? They just use different reagents. So that's the only thing that we're worried about there, okay? Okay, so now what I want to do is come up here slightly, and I want to do a summary of what we've talked about so far, because we've talked about a lot, right? So I think that it would be important to kind of summarize this, all right? So with a 2-degree alcohol, if we're taking a 2-degree alcohol and turning it into a ketone, well, this is always what happens, right? 2-degree alcohols always become ketones. So what can we use to turn a 2-degree alcohol into a ketone? Well, in this video, we talked about the very first reaction was bleach with acetic acid. That was one way we can do it, right? We can also use the 2 we just discussed, Swarin oxidation, and DMP. And then the final two, which contain chromium, are chromic acid, or the Jones reagent, and PCC. Okay, so these are all five that we've talked about, and they can all five do this, right? Everything turns a 2-degree alcohol into a ketone. However, if I want to turn a 1-degree, let me be more clear. I'm going to write alcohol here. Sorry. So 2-degree alcohol and 1-degree alcohol. So if I want to turn this 1-degree alcohol into an aldehyde, then I have to use weak oxidizing agents, right? So what are my weak oxidizing agents? Well, if I take bleach and use tempo with it, right? That's one way I can do it. Again, the two we just discussed, the Swern oxidation and DMP, are two more. And then finally, the last way I can do it is with PCC, right? Because chromic acid is a strong oxidizing agent, so it's not going to turn it into an aldehyde. Okay. And then finally, if I want to take a 1-degree alcohol and turn it into a carboxylic acid, right? So I want to fully oxidize this thing. Then I can use bleach with tempo, but it has to be excess bleach with tempo. And then the only other way I can do it is with chromic acid. Okay. Other than that, Swern, DMP, PCC, all those are weak, right? So they won't be able to do this. And then I said I would mention it, so I am mentioning it. 3-degree alcohol. No reaction. Do not forget that, okay? I don't care if you're using bleach with tempo, bleach with no tempo. I don't care if you're using Swern, DMP, PCC, or chromic acid. I don't care. You will never oxidize a 3-degree alcohol. If the alcohol is 3-degree, nothing's going to happen, okay? It doesn't matter what the molecule looks like. It doesn't matter anything. The 3-degree alcohol is not going to get oxidized. It is not possible, okay? So if you see a 3-degree alcohol, immediately write no reaction, okay? Immediately write no reaction. If it's the only alcohol in there, you know, some molecules can have more than one alcohol, so maybe you're only oxidizing one, okay, whatever. But like I said, no reaction, okay? But I think this is a good summary. You know, 2-degree alcohols to ketones, there's our 5 things. 1-degree alcohols to aldehydes, there's only 4 ways to do it, right? And then carboxylic acids, there's only 2 ways we can do that. We can use excess tempo or chromic acid, excess bleach with tempo or chromic acid. That's it, right? So that's all for oxidizing everything. Hopefully this video was helpful. In the next one, we're going to be talking about converting alcohols into other molecules. So like converting an alcohol into an alkyl halide, right? So that's what we're going to talk about in the next video. So hopefully join me for that. I appreciate you watching this. Hopefully it was helpful, and I will see you next time.